So now we're going to look at a little more complicated biomechanical behaviors of bone. The first common one, fatigue. Fatigue is defined as the gradual failure caused by cyclic loading, a loading that constantly repeats. And we can calculate how long a material, in this case a bone, can withstand that repeated loading and at a given stress, how long it can stand it until it fails. We call this the SN curve, the stress versus cycles curve, and it shows the cycles of failure. The formula is the stress is equal to A times the number of cycles to the power of B. We can see B here is that slope of the line, the curve. We call this a curve. Usually we made it a straight line. This is a curve, as you can see, exponential, but this graph has been made linear, a linear relationship, because we took the log of stress over E, and we have the log of N over here. So how do we understand it? So basically this says that a stress at this point, we can convert from stress to this logarithmic form. If we find a stress at this point, and we trace the line to the curve, in this case a straight line, and then we go straight down that point, this will tell us how long the loading can be applied before failure is bound to occur. There is, however, a limit, and you can see there's this dashed line over here, and this is the limit to failure. So any load that has a stress less than this portion, regardless of how repeated the load is, if the stress is below this point, the material will never break. It's called unbreakable. Eventually it may be, but scientifically it's not important at that moment. The next important one is creep. Creep is defined as time-dependent deformation. In other words, a deformation that's caused merely by time, just by letting the stress, leaving the stress applied. With constant stress. That is, if you would have a stress applied to any object and you wait for enough time, you wait for a long time, usually it can take a year, like years, sometimes even decades, eventually that stress, by being applied to that material, will cause the material to strain further than it was calculated to be initially when you first applied the stress. Even if it's in the elastic region. So we have here what's called the triphase diagram, and we have strain versus time. So now we're leaving stress as a constant. We are applying some stress, and we're leaving that as a constant. We can see that initially, as time moves on, it will strain a little faster until it reaches this relaxation phase. It will just hang on this point for a long time, and this time from this end to this end can be years, it can be 10 years, and it can be much more. Totally depends on the material, and it can be even less, like a year or less. But this will take time to relax at this moment, but then after this point, on the third phase, it's just gonna increase to failure. Minor's rule. And this Minor's rule is really important to biomedical applications, because it allows us to convert very fluctuating stresses and have an approximate when the material is going to fail. Because if you go back at this point, we're applying a constant stress over here, but in biological situations, we don't really know the cycle stress that's going to be applied. It may be like, let's say, 3 Pascal, and then the stress will just be 10 pascals, and then back to 4, and then 3, and it can stay like that, and it can be like in this case over here, cyclic, repeats a certain amount, but then it also has another very high spike, and that high spike repeats, but not as much as the lesser one. So how do we know how long this is going to last? Well, Minor's rule states that failure would occur when you sum the individual fatigues, the individual, in this case, n over cycles, to give you 1. When it equals 1, when all these sum give you 1, you're going to have a failure. So as an example, just quickly between here, n is going to be equal to a, the stress over e to the power of b. You can see that's going to be another rearrangement of the previous equation over here, but it's in a different format. And this will help us work backwards when we try to find, when we try to solve for that failure. So let's give an example here. Okay, we have a stress applied at time n1, and this n is being repeated. It's going to continue repeating. But we also have a larger one, a larger stress that's repeated less frequently, and n2 is smaller. The time it takes for the cycle to repeat is smaller. So the question is, how would we find out how many cycles, how many repeated of these cycles can it stand? Can, let's say, a bone stand before it fails? So let me just restate that again. We have a cycle that's like this, constant, a little constant, and it spikes, and this thing is going to repeat a little bit, and it spikes. Now this is not a constant stress, but how do we find out how long it will last? So if we were to use Minor's rule, these are the 4 steps you can use. The first one is find the log of the stress over elasticity, modulus of elasticity. So we're going to find for 1 and we're going to find for 2. We're going to log that. Then we're going to go to the graph, and this is the graph method. I'll show you the formula method later. You're going to go to the graph, and you're going to find the point. So if let's say negative 2.3, let's say over here, then we're going to follow to here and see what number it sits here. In this case, let's call that 2. So this is the value we're going to use. We now know that Ni is 2. But we already know what N1 is. So then we already know what the small n1 is. So the large n1 would be, we calculated 2, and the small n1 is, let's make that up, 1.5 seconds. I don't know, 2 seconds. 2 over 2, that will give you 1. Actually, my bad. The log of n over here is 2. The log of n over here is 2. You're going to have to take the log of that, the inverse of that. In other words, 2 must be equal to log of n. How do you solve that? Well, then if I take to the power of both sides, the log 10 to the log 10 of n is going to cancel out. So we're going to have 10 to the 2 is equal to n. These are going to cancel out. It's like e to the ln. These are going to cancel out. So we have 10 squared, and that will come out to 100 over here. But the n's will stay the same. I just plug in the n's. I have to find the small n I plug in, and the large n's I just have to find from the graph. And then I'm going to have a number. It won't equal to 1. It's probably going to equal to 0.2. It's probably going to equal to 0.1. So my question is, what type of cycle, what type of n will give me a cycle equal to 1? We're trying to find NF. We're trying to find some number of cycles, that will give me this number equal to 1. Well, if I inverse this, if I inverse the number I get, let's say I got 0.1, if I get, let's say this sum is equal to 0.1, that means that I can allow 10 more of these cycles. 10 more of these cycles can occur before failure occurs. So then the actual number of cycles, if I inverse this one, would be 10. So I can have 10 of these cycles before failure occurs, because Minor's rule states that I need to have it equal to 1 before failure occurs. And as I said before, if you don't want to draw a graph, or like there's no time to draw a graph, you can simply use this formula. So it'll be the same. You find the log of this one. Sorry, you just find this one, plug it in, and then you would find your n, capital N, and you're gonna use the same method. You're gonna get it equal to some number, usually maybe 0.1, maybe 0.2, and you're gonna see, well, how much more of that can happen before it does equal 1. That is what NF is. The cycles to failure. The combined cycle to failure. All of this, how much of all of this can happen before it fails.